Okay, it is recording now.
Sir, it is recording.
Okay, then I need to share my screen 1 second.
Good evening, sir.
Good evening, good evening. You can see my screen now?
Yes, sir.
Assignment 10.
Yes, sir. Assignment 10.
Okay. But that is not the screen that I have. So what is happening? 1 second. I have to stop sharing. Share the screen. Okay, you can see a question mark now.
Yes, sir.
Okay, I hope it is working. It doesn't give me further problems. Okay, there are only 10 participants there. Somebody said there was.
Good afternoon, sir.
Good afternoon. Good afternoon.
Sorry for the late, sir.
No, that's okay. So you had a test just now?
Yes, sir. But it finished now.
It's over. I can start my discussion.
Yes, sir.
Sir, I'll message on WhatsApp group and inform them if somebody want. Like,
Well, maybe I should wait for 2 or 3 more minutes so that if somebody wants
yes,
to,
sir.
they can join. Yeah, I seem to be having continuously problems. Now it is not working. 1 second. Let me see what is happening.
Okay, sir.
Okay, I hope you can see the screen, white screen.
Yes, sir.
Yes, sir.
So I'm sorry, today it seems to be problems all the time. Anyway, I hope we will go without any further problems. So we will start with assignment 10. First question. Can you see whether it is being recorded? Does it say?
Yes, sir.
Recording.
Yes, sir. It is recorded.
Okay, it is being recorded. Okay, being recorded. So for the assignment 1, question A part is actually 5. You are given 5(1) is equal to C1 into S plus square root of 2 times 2pz, and phi2 is equal to C2 into 2s plus C3 into 2pz. You are asked to determine the values of C1, C2, C3. Correct?
Yes, sir.
So the way to do that is actually you say, okay, phi1 must be normalized. So integral of phi1 square d2 must be equal to 1. And if you substitute it for phi1 in here, what you will get is integral c1 square s plus root 2 times 2pz whole square d2 is equal to 1, which means that c1 square into, if you square this, you will get the integral of s square. Then you will get the integral of 2pz square plus you will get integral of s into 2pz into 2. So these are the integrals that you will get. And this must be equal to 1, but you know that s and pz are orthogonal, so this integral will be 0. Pz atomic orbital is normalized, so this integral will be 1. S orbital is normalized, so therefore this integral will be 1. So C1 square. Oh, I made a mistake. There must be
Root 2.
a 2 here and a root 2 here.
Yes, sir.
So therefore what happens is that C1 square into 1 plus 2 must be equal to 1, which means that C1 must be equal to 1 by root 3. Correct?
Yes, sir.
Yes, sir.
Then phi2 must be normalized. What does it mean? It means that C1 square plus C3 square must be equal to 1. Is that okay?
Yes, sir.
Yes, sir.
And so you have one equation now. Then phi1, integral of phi1, phi2, what should it be?
0.
0.
0.
So if you work this out, what will happen is that you will get C1 into C2 plus, correct me if I am making mistakes, root 2 times C3 must be equal to 0. Is that okay?
Yes, sir.
And therefore, C3 must be equal to minus 1 by root 2 C. Because you say C1, you can cancel. C1, you know, it is 1 by root 3. So therefore, this must be equal to 0. So if you work this out, this is what you get. And eventually, if you worked out, what will happen is that phi2 will be equal to 1 by root 3 root 2 times 2s minus 2pz. This is the final answer. If you want me to work out, I shall work out, but it is fairly simple. I have given you all the steps. So these are the two orbitals. The first one will be phi1 equal to 1 by root 3 2s plus root 2 times 2pz. And the second one, which is which is normalized and orthogonal to this, will be so much, but with a negative sign. Why the negative sign? The answer is that phi1 and phi2 must be orthogonal. Without the negative sign, it is not going to be, the orbitals are not going to be orthogonal. Any questions on this?
No, sir.
Yeah, think about it. I have something to do. Let me just try to do that. 1 second. Okay. So the next part is actually you are asked whether the two orbitals are equivalent. And what is your answer?
No, sir. They are not equivalent.
They are not equivalent. Why?
Sir, because we are getting one combination as 2s minus 2pz and the with the different coefficients also, and the contribution will be different for phi 2 and phi 1 from s and pz orbitals.
That's correct. You see, if you look at this, what happens is that you see here you have square root of 2, while here you have 1 here. 2s is multiplied by 1, while here it is square root of 2. So therefore, the amount of 2s contributing to phi 1 and phi 2 are different. Correct? Similarly, if you think of 2pz, here there is square root of 2 and there it is minus 1. So therefore, the amount of contribution of 2pz to each one of these orbitals is different. And therefore, the two orbitals cannot be equivalent. They are not equivalent. Okay, then the next thing is actually you have to make plots of these orbitals. This is 2pz and that is 2s. So this is the way it is. If you wanted the first orbital, what will happen? You will multiply, if you wanted this orbital, which is phi 1, you will multiply 2pz by root 2 and then simply add 1 to s. That means you see the contribution of 2pz is more, so therefore this orbital will look like 2pz more. So effectively what will happen is that this lobe, see here the 2pz has a positive lobe, so and the 2s also has a positive, so also is positive. So therefore when you add, when you multiply by root 2 and add, what will happen is that the contribution of 2pz will be more and therefore this orbital will look like that. This will be plus and that will be minus. Or even this negative lobe may be very small actually. Oh no, it will be fairly large because 2pz has a larger contribution. Okay, then this is actually phi 1 and what will happen, phi 2 will have a larger contribution from 2s, so therefore it will look something like this. And the nucleus will be somewhere here. And here the nucleus will be somewhere here. So even though the two orbitals actually, with the way I have drawn it, they appear to be similar, but their shapes are not the same. Their shapes are a bit different because of the fact that 2s and 2pz do not make the same amount of contribution to these hybrid orbitals. Okay?
Yes, sir.
Okay, the next question is actually about electronic configuration of diatomic molecules and calculating the bond order. I don't think I need to discuss that, should I? Because this should be very familiar to you.
Yes, sir.
Carbon,
Yes, sir.
the bond order will be 2. Oxygen, the bond order will be 2. B2 also, I believe the bond order is 2.
Sir, it is 1.
Okay. One second. Let me
Yes,
just
one.
check that. No, it is actually equal to 2. Because the electronic configuration is 1 sigma G with 2 electrons, 1 sigma U star with 2 electrons, 1 pi with 1 pi X with 2 electrons, and 1 pi Y with 2 electrons. These are bonding orbitals.
Sir, it will be 2 pi.
Sorry.
Sir, it will be
Sir,
2 pi.
pi has the one electron only. Pi x has 1 electron, pi y has 1 electron.
Second, boron is how many electrons? Each boron atom.
1s2, 2s2,
Pi.
2p1.
5 electrons.
So before it will be 1, that means 3 valence electrons, right?
Yes, sir. 3 electrons.
So in
Yes,
total,
sir.
it has to accommodate 6 electrons. So therefore, 2 here, 2 here. Yeah, this is correct. I have made a mistake in copying from somewhere. So therefore, this is 1, and therefore the bond order is 1. Thank you. That is correct.
Yes.
Okay, then you are asked to do a cell molecular orbit calculation for, this is question number 3. You have to do a Huckel molecular orbit calculation for this species. This is a fairly lengthy exercise. Let me put the carbon atoms as 1, 2, 3. So what will be the Huckel matrix?
So x1, 1.
X1, 1, 1, X1, 1,
1, 1x.
1x.
then C1, C2,
C1, C2, C3.
is equal to 0.
Yes.
So,
Hello.
so therefore, if you wanted to find out the molecular orbital's energies, then you have to take the determinant of this matrix. and put it equal to 0. Okay?
Yes, sir.
And what is the result?
Sir, x equals to x minus 1 square into x plus 2 is equal to 0.
Yes, sir.
X minus 1. Well, actually what you get is, it is
Plus 1 and minus 2.
Yes, sir.
minus 1 into x minus 1 into x plus 2
Plus 2.
is equal to 0. This is what you will get, which means that the solutions are actually x is equal to 1. That occurs 2 times, so x is equal to 1 and minus 2. These are the values of x. But remember the definition of x, it is defined to be alpha minus script t by beta.
Beta.
So therefore, if x is equal to 1, you will get alpha minus script t by beta is equal to 1, which implies that script t, the energy of that molecular orbital, must be alpha minus beta. But this will occur 2 times. So one more alpha minus beta. Then when x is equal to minus 2, alpha minus script t by beta is equal to minus 2, which implies that script t must be equal to,
Alpha plus 2 beta.
and remember beta is negative, so therefore alpha plus 2 beta is low, while alpha minus beta is higher. So therefore, if you do the molecular orbitals, what will happen is that you will get a single molecular orbital having an energy of alpha plus 2 beta, and you will get 2 molecular orbitals having the same energy, which means that they are degenerate. They both have the energy of alpha minus beta. This one corresponds to x is equal to minus 2, while this will correspond to x is equal to 1. So the energies of the molecular orbitals are given here, alpha plus 2 beta, then alpha minus beta occurring 2 times, and the molecular species that is given is positively charged. That means you have the cyclopropenyl cation. Cyclopropenyl cation has 2 pi electrons. Therefore, those 2 pi electrons will go and sit here. And so you have a closed shell because it is the cation. And further, if you think about it, it actually obeys the 4n plus 2 rule. Because this is a cyclic ring system having how many electrons?
2 electrons.
2 electrons. And that is a case, special case of 4n plus 2 if the n is equal to 0.
0.
So therefore, this is actually quite stable, and the molecular orbital calculation tells you that the energy of the system is low because the orbital with energy alpha plus 2 beta has 2 electrons in it. So therefore, the total energy of the system will be 4 alpha plus, sorry, not 4 alpha, but 2 alpha plus
4 beta.
so it will be 2 alpha plus 4 beta. In comparison with that, suppose you think of one of the resonance hybrids. You see, for example, this is a resonance hybrid. And this resonance hybrid, in fact, in valence bond theory, you say that there is a resonance hybrid of 3 possible structures. These are the three possible structures. Now, if you think of this particular structure has a one bond, one double bond. And this is actually, according to our understanding, this is ethylene-like bond. And you should remember that the energy of the ethylene-like bond is actually 2 times alpha plus.
2 alpha plus beta.
So therefore, energy of any one of these structures is 2 alpha plus 2 beta, while the actual energy of the system is 2 alpha plus 4 beta, which is lower. And therefore, we say that there is a resonance stabilization, and that resonance stabilization is actually equal to minus 2 beta. Because the energy difference between this and that is minus 2 beta, and that is the resonance stabilization of cyclopropenyl cation. Is that okay?
Yes, sir.
So this resonance energy, usually in molecular orbital theory, you refer to that as the delocalization energy. Okay?
Yes, sir.
Yes, sir.
Then we have the problem of finding the molecular orbitals. You know that x1, 1, 1, x1, 1, 1, x, multiplying C1, C2, C3 must be equal to 0. So if you wanted to find out the first molecular orbital, which has x is equal to minus 2, right?
Yes, sir.
Yes, sir.
Then what you have to do is you have to put minus 2. Have I made a mistake? Minus 2, 1, 1. 1 minus 2, 1. 1, 1 minus 2. C1, C2, C3 is equal to 0. Okay, this is fine, there is no mistake. So you have three equations. What are the three equations? You have minus 2 into C1 plus C2 plus C3 is equal to 0. Then C1 minus 2 C2 plus C3 is equal to 0. Then C1 plus C2 plus minus 2C3 is equal to 0. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
So now you have to solve. How will you solve?
It is coming.
Well, there are different ways of solving, but you see, let us say, see, for example, you can subtract the second equation from the first. What is the idea? The idea is I want to cancel C3. So if you subtracted the second equation from the first, what is the result?
Minus 3C1 is
Minus 3C1 plus
3C2
3C2.
must be equal to
0.
Implies that C1 is equal to C2.
Yes, sir.
Similarly, if you subtracted the third equation from the second, what will happen? You will get a similar result which says that C2 is equal to C3.
Yes, sir.
Therefore, you get the result that C1 must be equal to C2 and that must be equal to C3. Is that okay? C1 is equal to C2 and C2 is equal to C3. This means that all the coefficients are
Equal.
Equal.
and further the orbital is normalized. So your orbital is actually C1, let me say What should be my notation? I don't remember the notation in the lectures. Is it called P1, P2, P3, the p orbitals?
Yes.
So this is your molecular orbital, and so if you took the square of this and integrated over the entire space, the answer must be 1. So when you square it, you will get C1 square, and then you will get P1 square integral of D2. But that the P1 is an orbital that is normalized, so therefore this integral will be 1. So therefore the first term will be simply C1 square. Similarly, you will get C2 square plus you will get C3 square is equal to 1. Why? Because the cross terms involving P1 and P2. Remember, the overlap integral between P1 and P2 is assumed to be 0.
0.
Therefore, none of the cross terms actually contribute. And therefore, the only terms that are there are C1 square, C2 square, and C3 square. So they must be added up to give you 1. But they are all equal. So, for example, C2 is equal to C1 and C3 also is equal to C1. So therefore, the result is 3C1 square is equal to 1, which implies that C1 must be equal to 1 by root 2. And therefore, the bonding molecular orbital, which I call phi1, has this result. It is 1 by root 3 into P1 plus P2 plus P. So this is the most bonding molecular orbital. Any questions on this?
No, sir.
Then the next molecular orbital, let me call it phi2. It will be equal to C1 P1 plus C2 P2 plus C3 P3. These C1, C2, C3 are the coefficients of this molecular orbital, and they are not the same as the C1, C2, C3 in the previous molecular orbital. Coefficients will be in general different. So what will this C1, C2, C3 satisfy? Well, in this case, X is equal to how much?
1.
X is equal to 1, so therefore you will get 1, 1, 1, 1, 1, 1, 1, 1, 1. C1, C2, C3 is equal to 0, right? This is what you will get.
Yes, sir.
And if you multiply it, what will happen? You will get C1 plus C2 plus C3 is equal to 0. In fact, even though you think that you may get 3 equations, they are all the same. So all that it says is that C1 plus C2 plus C3 must be 0. Actually, I would have liked to have more equations because I have 3 unknowns here, right?
Yes, sir.
But from these things, I have only one equation, but I can get one more equation. What is that equation?
By putting one of them equals to 0.
Yeah, that is possible. But even before that, we have one more equation because that equation says that this function must be normalized.
Yes, sir.
Yes, sir.
Normalization means C1 square plus C2 square plus C3 square must be 1.
1.
So now you see we have only 2 equations and we have 3 unknowns. So therefore, the system is it has many solutions actually. And if you are interested in one solution, then what you can do is you can say, okay, I'll put C3 equal to 0. But you could have as well put C2 is equal to 0. You would have got another solution that also is perfectly acceptable. Or you could have put C1 equal to 0, then you will get another solution. It looks different, but that also is perfectly acceptable. So let us choose C3 is equal to 0 as our choice, in which case you will get C1 plus what is the result? C1 plus C2
Plus C2 is equal to 0.
is equal to 0,
C1 square plus C2 square to 1.
which implies that C1 must be equal to minus C2, and here C3 must be 0. So therefore C1 square plus C2 square must be equal to 1. And if C1 is equal to minus C2, what will happen?
2C1 square is equals to 1.
You get 2C1 square is equal to 1, which implies that C1 must be equal to 1 by root 2.
Root 2.
And
Then
C2
C2 is equal to minus 1 by root 2.
must be equal to minus 1 by root 2. And therefore, this molecular orbital, which I will call phi 2, must be 1 by root 2 times P1 minus 1 by root 2 times P2. Is that okay?
Yes, sir.
Yes, sir.
Then the next molecular orbital, which we will call phi 3, is C1P1 plus C2P2 plus C3P3. Now this must be normalized, which means that C1 square plus C2 square plus C3 square must be
1.
1.
And then what else do I have? I have C1 plus C2 plus
C2 plus C3 is equal to 0.
C3 is equal to 0. This is given. And in addition, we know that this orbital phi 3, we would like it to be orthogonal to
Phi 2.
phi 2.
And
And therefore, the orthogonality of these two, how will you determine them, guarantee them? You have to
phi
multiply
2 into phi.
phi 2 by phi 3 and integrate over the entire space. And the answer is, and integrate over the entire space, the answer must be equal to 0. So therefore, if you did that, this phi 2 into phi 3, if you integrate over the entire space, what you will get is C1 into 1 by root 2 minus 1 by root 2 times C3. No, 1 by root 2 times what?
C2.
C2 must be equal to 0, which implies that C1 must be equal to
Minus C3.
C3.
no, this is C2.
Yeah, C2.
So therefore, C1 must be equal to
C2.
C2. So now we will put this back in here. And further, you can use this. C1 plus C2 plus C3 must be 0, which means that 2C1 plus C3 is equal to 0. Why?
Okay, I found this on the web for is equal to sin y. Check it out.
Should I repeat?
Interesting question.
Siri is making no sense.
He will not stop.
I have to find a way of stopping it. I have not tried to do that, but anyway, I will not try it now. But at least I can reduce the sound. Let me see. Okay, well, you see, in that process, when I tried things, my transmission has stopped. So where were we? Well, let me just repeat. Phi 3 is given by this expression. Then phi 3 is normalized, which implies that C1 plus square plus C2 square plus C3 square must be equal to 1. Further, the matrix equation was x1, 1, x1, 1, 1, x. Multiplying C1, C2, C3 must be equal to 0. But x is equal to 1, so therefore all the diagonal terms are equal to 1. So you get 1, 1, 1. And if you multiply this matrix, this row with that column, you will get the result C1 plus C2 plus C3 is equal to 0. That is how you got this. And then you say that this molecular orbital must be orthogonal to the previous molecular orbital. It has to be orthogonal to this orbital. That implies that C1 into 1 by root 2 minus C2 into 1 by root 2 must be equal to 0, which means that C1 must be equal to C2. And if C1 is equal to C2, you can take that and put it in here. So you will get what? You will get 2 times C1 because you have C1 plus C2. C1 is equal to C2, so therefore C1 plus C2 is actually 2 times C1 plus C3 is equal to 0, which means that C3 must be equal to 2C1 minus 2C1, right?
Yes, sir. Minus 2C1.
So therefore, we have now enough material to do the calculation. C1 square plus C2 square plus C3 square must be equal to 1. C1 is equal to C2, so therefore I can say this is actually C1 square. C2 is equal to C1, so therefore that also is
C1 square.
And C3 is equal to minus 2C1, which means that the square must be C3 square must be
C1 square.
4C1 square must be equal to 1, correct?
Yes, sir.
Which means that 6C1 square is equal to 1, which implies that C1 is equal to 1 by root 6. So therefore we have determined C1.
C2 will be same.
Then we are already done because C1 is equal to C2, so C2 must be 1 by root 6. And what about C3?
2 root
Minus 2 by root 6.
minus 2 by root 6.
Minus 2 by root 6. So these are the 3 coefficients. So therefore, we have found the expressions for the molecular orbitals. Even though the assignment does not ask you to give the shapes of these orbitals, let me just draw them. This is the most bonding molecular orbital. So these interact, and you get the most bonding molecular orbital. Is that okay?
Yes, sir.
Because
Yes, sir.
of the form phi1 equals 1 by root 3 P1 plus P2 plus P3. Then how about the next molecular orbital, phi 2? It is 1 by root 2
by root 2 P1
P1
minus 1 by root 2 P2.
minus P2, and it has no contribution from P3. So
Yes.
it was our atom number 3. Let me look at what I had written. Yeah, the top atom was, top carbon atom was called atom number 3. So therefore, the molecular orbital has no contribution from P3. This orbital on 3 has no contribution. This P1 is occurring with a positive sign, so therefore you will have a positive lobe here and a negative lobe there. And P2 is occurring, remember, with what sign?
Negative.
Negative.
Sign, so therefore you have
Negative.
Minus.
by minus 1, so therefore you will get minus here and plus there, and therefore this has a node. You notice there is a node. This is actually the node, and that is why it is antibonding. This is phi 2. Then the third molecular orbital, phi 3, is actually 1 by root 3 P1 plus.
So 1 by root 6 P1.
Thank you. Thank you. As I usually say, that makes me quite happy. 1 by root 6
P1 plus P2 minus 2 P3.
minus 2P3. So therefore, if you look at this, you see P3 has a large contribution in comparison with P1 or P2. So therefore, how will it occur? But it is occurring with a negative coefficient.
Yes, sir.
So therefore, if you, okay, I will draw this molecular orbit in this fashion. This has a big contribution from P3, and it is
Minus plus.
so therefore originally the orbital was positive here, but because of the multiplication by minus 2, this becomes a huge negative lobe. This becomes a positive lobe. Then you have P1 and P2 occurring with the same sign, so you will get, but it is smaller. So that is how the molecular orbital is. If you wanted a slightly better picture, what will happen is that it is rather difficult to draw, but this is probably a better way of drawing the molecular orbital. I hope this is understandable, is it?
Yes, sir.
Yes, sir.
These two combine and you get this rather this shape that I have put. And these two combine and you get this shape that I have put. Then this one, let me use a different color, is here. And this one is this law. So that is how the molecular orbit is. And how many nodes does it have? Yeah, but it is, you would expect that a node in this fashion, right? A node like that and a node like that.
Sir, there will also be a node like on the plane of.
That's there. I'm not talking about that node. You see, what happens is that this is actually a node of this shape. It is a nodal surface. It is not a plane.
Okay, sir. Okay, sir.
Unlike the previous orbital. And then, of course, all these orbitals have a node. What is that? That is the plane of the molecule. The plane of the molecule is a node for all the pi-type orbitals. So that's why I did not talk about it separately.
Yes, sir.
Okay, I think that covers the assignment. Let me just check. Any questions on this assignment? If not, we will go.
Sir?
Yes.
So in this matrix we will make which we make here x1 1. If and in any column or row if there is -1, what it means?
What is?
What it means if there is any -1. Suppose if we have the matrix x1 -1 like this.
Okay.
And the rest is same like 1 x1
No,
1 1 x.
that doesn't happen. This does not happen with Euclid matrices. The Euclid matrices
Sir,
are
but
always,
okay.
always symmetric.
Okay.
If you look at this matrix, it is not a symmetric matrix. While Euclid theory, see any Hamiltonian, any matrix that you study in quantum mechanics will be usually a Hermitian matrix. And these are real matrices, so if you say it is Hermitian, it actually means that they are symmetric matrices. So you cannot have a -1. If you had a -1 there, then you have to have a -1 here also. Okay?
Sir, but there is a yes, sir. So,
Yes.
but what is the meaning of this -1?
This is a question that needs lot of explanation. You have my lecture notes, right?
Yes, sir. Yes, sir.
You have.
But in the lectures, there is no about -1.
No, it is not there. Because I told you the lecture notes contain more material than is needed for you.
Yes, sir.
There are systems which are referred to as Mobius systems. This particular matrix that you are telling me is an example of a Mobius system. The way this arises is explained in the notes that I have given you. So if you want to understand it, you please go ahead and read it. And in case you have read it and you do not understand, you can ask me. Because you see, if I discuss this, it will take me half an hour.
Yes, I will.
Have
I
a
will
look
learn.
at the notes, and you will not find
Yes, sir.
this in other books actually, because you see, this is a rather new topic in ethical theory. New meaning, it's about 15 years old.
Okay. Also, I will see. Thank
Okay.
you.
Who asked me this question?
So, Jatin.
Jatin. Okay, Jatin. Thank you. I mean, happy that you are curious and.
Thank you, sir.
Okay. Any other question? If not, I will go to the quiz questions. So quiz A part. First question is write down the full wave function for S2 according to MO theory. So it is a fairly simple question. So what does MO theory tell you? It says that there is one electron in sigma. Well, there are two electrons in sigma G1s. So if you wanted a more explicit form, you will say sigma G1s, first electron is sitting there. Sigma G1s, the second electron is sitting in the same molecular orbital. So therefore, let me explain to you what is the meaning of this. This means that the wave function is a product of two sigma G1s orbitals. Why is it a product? Well, the first electron is sitting in that molecular orbital, and that molecular orbital, in that molecular orbital, one is there, which means that you have to put in the position coordinates of the first electron. And then into the second molecular orbital, you have to put in the position coordinates of the second electron, and then you take these two molecular orbitals. This has R1 and that has R2 in it. You multiply these two, and that is the psi molecular orbital. But this is not complete because this is only the spatial part, because this is only the spatial part of the wave function. And so what will happen if you have a molecular orbital and if you put two electrons into that molecular orbital, the two electrons will be
Positive spin.
it will be having opposite spin. They will
Yes,
be
sir.
paired, and for a pair of electrons having opposite spins, you see the wave function for the spin part of the wave function will be 1 by root 2 times alpha 1 beta 2 minus beta 1 alpha. So this will be the wave function. This is the spin part of the wave function. All that it says is that you have a singlet stage obtained by the pairing of two electrons. So this is the spin part and that is the spatial part. The spatial part, as you know, is symmetric because if we interchange the electrons 1 and 2, the function doesn't change. And the spin part, if you look at this, if we interchange the 1 and 2, what will happen to the spin part? Anybody?
Can you
Say,
please repeat?
sorry?
Can you please repeat? I can't hear.
Yeah, well, see, the question is, if you interchange the coordinates of the two electrons, what will happen to this product wave function? The spatial part is this.
Nothing will change.
If the spatial part is this one, right? This is the spatial part of the wave function. Instead of this 1, you can put 2, and instead of 2, you can put 1. Instead of 1, you put 2, and instead of 2, you put 1. But then you will see that it is a product. So therefore, before you interchange and after you interchange, this part of the function does not change.
Change.
So it is symmetric under the interchange of the two electrons. But if you look at this function, and imagine you interchange the two electrons, what will happen to this function?
Same with the minus sign.
So the wave function will change. When you interchange the two electrons, the wave function will change sign. And this is required because the wave function has to obey the Pauli explosion principle. So when you write the full wave function, the wave function always has to satisfy the Pauli principle. What is the principle? It says that if you interchange the two coordinates of any two electrons, the wave function has to change sign. And so this whole wave function actually together along with the spatial part and the spin part satisfies the Pauli antisymmetry principle. I see that there is complete silence. So if you have questions, I shall be very happy to answer that.
That is clear now.
Okay. Now you look at psi valence bond. In psi valence bond, what you do is you say, okay, you have one SA orbital with one electron and one S B orbital with the second electron. But at the same time, you see, you can have the other configuration in which 1s A has the second electron, 1s B has the first electron.
First electron.
So therefore, this is your valence bond wave function. It is multiplied by a normalization factor. We will not worry about the normalization factor. And this is actually the wave function. This is what I refer to as the spatial part of the wave function. Is that okay?
Yes, sir.
Yes, sir.
And if you interchange the coordinates of the two electrons in this wave function, what happens to this function? What I am saying is you interchange wherever 1 is occurring, you put 2, and wherever 2 is occurring, you put 1.
So remains same.
It will remain the same. So therefore, this wave function as it is written is symmetric under the interchange of the two electrons, and therefore it doesn't satisfy the Pauli principle, but that is not a problem because you have the spin part. What is the spin part? The spin part should be antisymmetric, which means that it is the same as in the case of your molecular orbital wave function. It should be 1 by root 2 times alpha 1 beta 2 minus beta 1 alpha. So therefore, the total wave function will be the product of the spatial part and the spin part. The spatial part is symmetric under the interchange of the two electrons, while the spin part is actually antisymmetric under the interchange of the coordinates of the two electrons. Any questions?
No, sir.
Okay, for H2 molecule, the next question, I'm going to go over to the next question. For H2 molecule, what are the advantages of the simple valence bond theory over the MO theory? Okay. This is there in the lecture, so let me just list the points. Valence bond theory describes dissociation correctly. In molecular orbital theory, it does not. The valence bond theory bond length is better, if I remember correctly. And then bond energy is definitely better. Bond length you will have to check, I don't remember now, but maybe MO theory gives a better bond length, simple MO theory. Bond energy definitely, valence bond theory gives a better value for the bond energy. So these are the three advantages. With this bond length you can please check, it is there in the notes.
Yes, sir.
Any comments, questions?
No, sir.
Do you expect He2 to be stable? That is the next question, and definitely you don't expect, right?
Yes, sir.
Sir.
The answer also, because it's essentially a BSc level question.
Sir,
Yes.
Akash this side, sir. Sir, in the second question, can we mention about the ionic contributions which it take MO theory?
That is actually a disadvantage.
Yes, sir.
You can,
So can we mention that?
you can say that MO theory has equal contribution from the
Ionic and
Ionic
covalent
and covalent.
structures.
absolutely fine. But then you will have to say that valence bond theory has no contribution from ionic.
Yes, sir.
That is fine. That is better actually.
Okay, sir.
Yes.
So question number 3, He2 molecule, do you expect it to be stable? I'm sure this is a simple question that you definitely know the answer. This is not stable. Why? Because if it was formed, then the electronic configuration will be 1 sigma G with 2 electrons.
So,
with 2 electrons and 1 sigma U star with 2 electrons. So the antibonding molecular orbital has 2 electrons. Bonding orbital also has 2 electrons. So bond order will be equal to 0, which says that there is no bond and the mode system is not stable. But if you remove 1 electron from He2 to get He2 plus, the electronic configuration will be 1 sigma G with 2 electrons, 1 sigma U star with only 1 electron, and bond order will be half. And you expect that the system is
having
Quite stable than
half
Fe2.
bond.
sorry,
He2 plus can
Fe2 plus is
exist.
stable.
He2 plus can He2 plus, which is an ion, can exist, and it does exist actually. You can make it.
Yes.
Okay, now we come to question number 5. The orbitals that are drawn in the question are these. So this is actually something like a 2p on the first atom and 2s on the second atom. And the question is whether these two can interact and give you molecular orbitals. What is the answer?
Yes, sir, they will interact to give.
They will interact. That is actually essentially determined by the overlap integral. So if the overlap integral between these two orbitals is non-zero, then there will be interaction. So here if you look at this, you see there is overlap. Where is the overlap? The overlap is in this region where the two orbitals overlap. So therefore, if you denoted the overlap integral by S, S is actually not equal to 0, and therefore these two orbitals will definitely interact. Now the question B, you have a 2s on this, and you have the same kind of 2p z orbital on the other atom. And the question is whether these two will interact, and what is your answer? Anybody? This is actually meant to confuse you.
Their interaction will be there, but destructive one.
Well, you see, this is a little tricky because you look at the overlap integral. Overlap integral, in this case, the overlap integral will be positive. Whereas the way these two orbitals are drawn, the overlap integral will be negative. But it doesn't matter because when the overlap takes place, or when the molecular orbitals are formed, the results are two molecular orbitals, correct?
Yes, sir.
One will be having 2pz with a positive sign, and the other will be having 2pz with a negative sign. Correct? So if
Yes, sir.
the way it is drawn, if it occurs with a negative sign, then what will happen is that then we can say, okay, there is a destructive interference or something like that, which will remove electron density from the internuclear region. But you think of the combination in which 2pz occurs with a negative sign. If it is occurring with a negative sign, what will
I
happen?
don't have an answer for that. Is there something else I can help with?
No, thank you.
Okay then.
So if it is occurring with the opposite sign, then what will happen is that you see this p or pz orbital will get multiplied by a negative number. which means that this on this side you will have the positive lobe and on that side you will have the negative lobe. And so therefore, whether it is the overlap integral is positive or negative, because there are these two possibilities, two possible molecular orbitals, one having positive sign and the other having negative sign, there will always be interaction and there will always be the formation of a bonding molecular orbital as well as an anti-bonding molecular orbital, and therefore even in the second case, in the B case also, you will have the formation of two molecular orbitals, a bonding and an anti-bonding molecular orbital. Is that okay?
So what does this negative then mean?
Yeah, well, you see that is, you definitely know that these signs are arbitrary. If I wanted, I could have, instead of putting a negative sign here, I could have put a positive sign and that is equally acceptable. Here I could
Okay,
not
sir.
put a positive sign. It is your choice. The sign of a wave function is your choice.
Okay, sir.
That's why I said this is actually meant to confuse you, because it is not likely that you will answer this correctly. So C part, you have a p orbital like this, and you have an s orbital which is like that. And what will happen? Can they form a molecular orbital? Can these two orbitals combine and form molecular orbitals?
No, sir.
Why?
S is 0 here.
Because the overlap, you see, if you think of the overlap, there is a positive overlap here, but there is an equivalent negative overlap, and therefore when you calculate the overlap integral, yes, will be equal to 0. Overlap integral means you multiply the first orbital with the second orbital and integrate over the entire space. So when you do the process of integration, you will have some regions where there is positive contribution, but there will be the same amount of contribution from the other regions where the product is negative, and therefore the overlap integral in this case will be 0. So this is not a bonding interaction. Then B part, you have a p orbital like that, and you have a d orbital which is like this. And the question is, will they interact?
Yes, sir. They will interact.
Why? Because you see here there is overlap. You have positive and positive, positive and positive. So the product is positive. Here you have negative and negative. But then the product is positive. So therefore, in this case, the overlap integral S will be greater than 0. It will not be 0. And therefore,
Yes,
the
sir.
orbitals will interact. Then E part, you have a p orbital, that is the shape, and you have a dz square type of orbital. This is the dz square, the negative log of dz square. So will the overlap integral be non-zero is the question, and obviously the overlap integral will be
Non-zero.
non-zero because you have the positive lobe overlapping with the positive lobe, and when you integrate you get a positive answer. And finally the F part. a p orbital interacting with a d z square. This is the negative load. So the question is, will the two interact? What is your answer? Essentially, what I am asking is the overlap integral 0 or non-zero? If it is non-zero, then there will be interaction.
So it is 0.
It is 0, why? Who is this?
So Sulekha.
Okay, Sulega, thank you. Your answer is correct. You have the contribution from this region, which is positive, but you have the contribution from this region, which is equally large but negative in sign. So therefore, these two regions are equivalent, except that the signs of the wave functions are different, and therefore, what happens?
So we call it as non-bonding or not bonding orbital.
I don't know, not bonding will be the best way.
Because they have written like non-bonding, because we have learned about 3 orbitals: bonding, anti-bonding, and non-bonding.
Non-bonding is a molecular orbital which is not involved in the bond formation. The molecular orbital is formed, but it doesn't contribute anything to the bonding, and neither does it contribute to anti-bonding. That is called a non-bonding molecular orbital. Now here you can say this is a non-bonding interaction. This is not referring to a molecular orbital. It is a non-bonding interaction. Why? Because this will not lead to the formation of a bonding and an anti-bonding molecular orbital. In the other case, you are actually talking about non-bonding molecular orbital. Molecular orbital is already formed. Here, no molecular orbital is going to be formed because this is a non-bonding interaction. Is that okay?
So everywhere I have mentioned like 3, there's 2, I have mentioned it as non-bonding orbital. So will that be like correct or like wrong? Because I've mentioned non-bonding, not like not bonding.
It would be better if you just said non-bonding interaction.
So but I've mentioned it as non-bonding already, like in that quiz.
Yeah, well, strictly speaking, it is not correct. So better in future you say non-bonding interaction.
Yes, sir. Yes, I will take care of it.
So this is actually A part, right? Question quiz 7, A part. Then quiz 7, B part. Can I proceed?
Yes, sir.
The first question is actually worked out in the lecture notes, right? So not in the lecture notes, but in the lectures itself, in the video lectures, the first question must be discussed.
Yes, sir, it is.
So therefore, it is straight away from the book or from the lectures.
I didn't find that on Apple Music.
It's okay, don't worry. So then you have to write down the Euclid matrix for 1,3-butadiene. It is a fairly simple question. I don't even know whether I should write it down. But anyway, just for the sake of completeness, you see 1,3-butadiene has a conjugated system having 4 carbons. Right, so therefore the Euclid matrix will be a 4x4 matrix. So tedious to write down. But what will happen is that you will have x1, 0, 0, 1, x1, 0. It is fairly easy. 0, 1, x1, and 0, 0, 1x. That's all. So this is the Euclid matrix for 1,3-butadiene. Is that okay?
Yes, sir.
Then cyclopentadiene. Dienyl anion is what is shown in the picture. Let me number these 1, 2, 3, 4, 5. And what is the way to write the Hückel matrix? Well, it's very simple. You see, if there are 5 carbon atoms, the Hückel matrix is going to be a 5 by 5 matrix. And of course, you know that along the diagonal, it is always X. So therefore, I first write the diagonal. Then whenever you have 2 atoms are neighbors, for example, 1 and 2 is a neighbor, so therefore in such a case you will have a 1 here, right?
Yes, sir.
Then 2 and 1 are neighbors, so therefore you will get the 1 here, then 1 here, then 1, 1, 1, 1, 1, 1. But then in addition to all this, 1 and 5 are neighbors in this particular case because it is a ring, which means that you will have a 1 here and you will have a 1 there. And all the other entries will be 0. So this will be the Hückel matrix for cyclopentadienyl anion. The only difference, you see, the major thing that you should notice is the absence of this one, which is not usually there in usual Hückel matrices for linear systems. If it was a linear system, this one and that one would not be there, right? Why? Because in a linear system, the structure would have the form 1, sorry, let me just put carbon atom 1, 2, 3, 4, 5. So in such a system, you say the 1 and 2 are neighbors, 2 and 3 are neighbors, 3 and 4 are, 4 and 5 are neighbors, that's it. But in a ring system, 5 and 1, 5 is bonded to 1, so therefore 5 and 1 are neighbors, and that is the reason why you get this additional 1 here, as well as that 1 there. Is that fine?
Yes, sir.
Yes,
So
sir.
in your notes, like a cyclopentadienyl cation, you have mentioned, but there it's 3 into 3 matrix.
Sorry?
Cyclopentadienyl cation. So there is 3 into 3 matrix like that. Can you explain it?
I don't know. Why do you say I have 3 by 3 matrices?
Sir, starter
It's in
allyl
your
cation,
notes.
not
No,
cyclopentadiene.
sir. Like in your notes, I don't know the exact page number, but it is there cyclopentadienyl cation, and it's written that we consider a ring of 3 carbon atoms, and then there is 3 into 3 matrix.
That is a mistake. I mean, when you see such a thing, you say that, okay, Professor Subhash is being stupid. If I write a 5-membered ring and below that, if I write the 3, let us now consider a 3-membered system. You see, that is obviously.
Yes, I could not understand while going for the preparation. I read it and so I was like not understanding this part, like how 3 into 3 matrix.
Can you send me the exact phrase and then I will correct it?
Yes, so I will send you a mail like after the class.
Yes. Thank you.
Okay.
The thing is, I think this is the first time that this much notes are being circulated, and therefore, even though I had been teaching for a long time, the notes I have almost never given. So because I didn't have them written, now I am writing them in the hope that I will be publishing the notes as a book. If there is such a mistake, please let me know and I will correct it.
Yes, I will.
Oh, I did something stupid because I was talking and doing it, and I let me see. My sharing is gone, I think. Okay, I hope we can see the screen.
Yes, sir.
Okay, sorry about that. Now, trimethylene methyl radical. It has 4 carbon atoms. Let me write the numbering in this fashion: 1, 2, 3, 4. So you will have X, 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 X. Because there are 4 carbon atoms, you have to put 4 X's. Then 1 and 2. Okay, I mean, maybe I'll rearrange. It is probably easier. Let me put it like this: 1, 2, 3, 4. 1 and 2 are neighbors, so you will get 1. 1 and 3 are neighbors, so therefore you will get a 1 here. 1 and
Sir,
oh no, sorry, that is not correct. 1 and 3 are not neighbors.
Yes, sir.
yes, sir.
You get 0. 1 and 4 are not neighbors, so therefore you will get 0. So therefore you will get 1 here, 0 there, 0 there. Then you think of 2 and 3. 2 and 3, they are neighbors, so therefore you will get a 1 here. Then you think of 2 and 4, they are neighbors, so therefore you will get a 1 here. And because it has to be a symmetric matrix, you see 1 and 1 there implies that you should have a 1 and 1 here. And then you worry about this one. This corresponds to which interaction? Interaction between 3 and 4.
3 and 4.
3 and 4, that is actually 0, so there is no interaction, direct interaction. So therefore you have a 0 here, which means that this is a 0 there. So this is the Euclid matrix for that system. Is this okay?
Yes, sir.
If you have any questions, you can ask me. Then the allied system, you see, we have discussed inner systems and we have been going on discussing for 1.5 hours now. Let me just tell you the results for the allyl system. Allyl system, the Euclid matrix is x1, 0, 1, x, 1, 0, 1, x. This is the Euclid matrix. Is that okay?
Yes, sir.
And if you expand, if you wrote the determinant, expanded it and found the solutions, what will happen is that you will get 3 molecular orbitals, one having the energy alpha, plus, what was the energy? I don't remember now. Let me just look at my.
Sir, alpha plus root 2 beta.
Okay, thank you all.
Yes, sir. Alpha plus root 2 beta and alpha minus root 2 beta.
Thank you. Alpha minus root 2 beta. And the
And
other
alpha, sir.
one is alpha.
Yes, sir.
That is correct. So naturally, this is bonding molecular orbital. You put 2 electrons in here. You will have a stable system, and that is what happens with allyl cation. And you don't have any electrons. Then electrons in this is a non-bonding molecular orbital. Okay, there was a question about non-bonding molecular orbitals. This is an example. Then this is an anti-bonding molecular orbital. Why? Because it is strongly anti-bonding. Then the expressions for the molecular orbitals, I shall again just write them. First molecular orbital is phi1. It is 1 by root 3 times p1 plus p. No, the p1 plus, no, that is not correct. If anybody has the correct expression, tell me. Otherwise, I am going to guess.
So I think it will be 1 by 2 P1 plus root 2 P2 plus P3.
Yeah, I'm correcting what I have written. So this is the orbital, correct? Thank you. Then in the molecular orbital, phi2 will be 1 by root 2
P1 minus P3.
P1 minus P3. And phi3 will be 1 by 2 P1 minus root 2 P2 plus P3. So these are the
Yes.
6 molecular orbitals. You can also draw pictures of these molecular orbitals. For example, phi1 will have large contribution from P2, so therefore the way you will draw it with this one will be here is carbon atom 1, there is carbon atom 2, and there is carbon atom 3. So therefore this will be the molecular orbital phi1. In comparison, the molecular orbital phi2 will be having a contribution from P1 and P3. So P1 will occur with a positive sign and P3 will occur with a negative sign. So therefore, this is how the molecular orbital phi2 will look like. And the molecular orbital phi3 will have a large negative contribution from the central carbon atom from P2. So therefore, you will find plus minus large contribution from the central one with opposite signs. So therefore, minus plus and plus minus. So this is the molecular orbital. Okay. Any comments or questions? Hello, you are all there?
Yes, sir.
Yes,
No.
sir. So no
Yes,
question.
sir. We are here. No question, sir.
Okay.
Sir, in this we have to, like in question, we have to find about allyl radical now.
That is not what is asked, right?
No, sir.
Allyl
Actually, my
cation.
question.
Allyl cation.
Okay, sir.
This cation, if you want to find what is the allyl radical, then what you have to do is you just put one more electron.
Yes, sir. Yes, sir.
And that will go and sit in this molecular orbital. That's it. And that is sitting in a non-bonding molecular orbital.
Yes, sir.
That is all. You can also talk about delocalization energy or resonance energy of the system. See, the normal valence bond theory will say that you have a double bond between these two carbons and a single bond between the other two carbons. So this is the normal valence bond theoretical picture. So you say it is positive. And you say that the system is a resonance hybrid of these two structures. So now you say that, okay, here there is a ethylene-like Dove system. So therefore, if you think of the energy of this system, it is just the energy of an ethylene-like system, so that is actually 2 times alpha plus b. But the actual system has a molecular orbital. The molecular orbital has energy alpha plus root 2 beta, right?
Sir.
Yes, sir.
And it has 2 electrons.
Yes.
Therefore, the actual system has so much energy, while the energy of a particular resonance structure is only so much. So the difference is actually how much?
Minus root 2 beta.
Minus root 2 beta. It is about minus 1.414 beta. So therefore, you realize that this is the resonance energy of cyclopropenyl cation. And this is a reasonably large resonance energy. Okay, any further questions?
So, like that cyclopentadiene cation, it is in page number 224.
Okay. Okay, I will look at it. Thank you. I'm
Okay, sir.
corrected. Sorry about the mistake.
Okay, sir.
Okay, if you do not have any more questions, we will be closing shortly. Now, the details regarding the quiz I will send you by email. I have discussed with Dr. Padmesh. He tells me that it has to be proctored, so therefore I am a little bit worried because many of you said that you do not have even a laptop.
Yes,
Yes,
sir.
sir.
How many of you do not have a laptop?
Sir, I don't have Sulekha.
Sir, I don't have.
So even like most of them are there, but they have not joined the class today.
Sir, only 4 students in our class don't have laptop.
Okay, yeah, but even if it is only one, you say it's a non-serial number, and therefore that is worrying. I think we will probably conduct it the same way that I have been conducting the test, but let me just confirm. I shall confirm this by email.
Okay, sir.
And also the duration, it is likely to be only for 2 hours in total. But that also I shall send an email and confirm.
Okay, sir.
Yes, sir.
Yes, sir.
Then other than that, I do not have anything more to say. This has been a rather unique experience. But I have never taught online, completely online. And I have not found it easy. It is rather difficult. Actually, physical classes would have been much more interesting, I believe. But anyway, you have seen my video lecture. Video lecture actually are not as good as the physical lectures, but that is probably the best that could have been done. I have not even seen you people physically. So when you came to the campus, I do not know when that is going to happen, because here in Kerala the situation is not good, unfortunately. But anyway, we have the vaccine on the horizon, and hopefully we will all be getting it within the next 6 months. So I would expect that you will be back in the campus within the next 6 months. That is my hope. Of course, you see, the director may want to bring you back sooner. Anyway, I'm not going to be there in the campus. I am at home because I have retired. This is the last lecture ever that I shall give, I think, in India IIT. And I have had a very long teaching career. When did I start? I started teaching in 1975, before all of you were born. So I had a fairly interesting, long teaching career, and this is the last lecture that I shall be giving. Of course, I mean, I may give other lectures elsewhere, but it is not likely to be teaching. Anyway, I hope to be continue to be scientifically active, and I wish I had met each one of you and got to know you all better. But anyway, I hope we will meet sometime in future when you are in the campus.
Yes, sir. We also hope to meet you soon because we also wanted to like have a physical interaction with you and
Yes.
get to know more. Yes.
Yeah, well, it is somehow easy because I have been teaching for such a long time, and always I have taught physically. I have not particularly enjoyed this because there were difficulties. Even today, you know, there were so many difficulties. Some connection is always lost.
Yes.
And today also I had to hurry a little bit because the portion was really too much to discuss in 1.5 hours. But I hope you have understood things. Anyway, these are things that are already familiar to you, I suppose, from the lectures. So anyway, I would like to thank you all once again.
Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
And any clarifications you want, you can send me an email.
Yes, sir.
Thank
Sure, sir.
Okay. Okay, then thank you all. And
Thank you,
continue
sir.
to the others.
Sir,
Yes.
sir, this recording, you will send it in the like on your YouTube link.
Yeah, I will put it in the YouTube. Let me see what is happening with the recording. Yeah, okay. I mean, I hope it is recorded and
Yes, sir.
It's recording, sir.
yes, now I have done this only a few times. I am worried that I may lose it if I just stop the recording. But of course, I shouldn't be losing, so I stop the recording. And then what happens?